people, hope we're doing well. This is the final video for the trig-based problems. This one's kind of fun. It shows up in several different books in several different ways. It's a writing a Ferris wheel question. So a Ferris wheel is 50 feet in diameter and its center is located 30 feet above the ground. If the wheel rotates once every 2 minutes, how fast is a passenger rising when he is 42.5 feet above the ground? How fast is he moving horizontally? Alrighty. Well, what we're going to do to make this easier is we're basically going to plot this almost like the unit circle. And basically, if we have something that has a diameter of 50, it has a radius of 25. And if that's the case, that means that if the center is 30 feet off the ground, then the bottom of it is 5 feet off the ground, right? Because this 5 feet, okay, let me switch over to a pen. This 5 feet and this 25 feet, because it's equal to this radius right here, is equal to that 30 feet off the ground. Okay. Well, that's first things. Okay, so that gets us to where we need to be for this. Now, it says, okay, the given is 1 revolution for every 2 minutes. Now, that is not exactly in terms of d theta dt, but we can get d theta dt from it because we can basically convert revolutions to radians. In 1 revolution, there are 2 pi radians. That, of course, is divided, and that is per every 2 minutes, so divided. So that winds up being pi radians per minute. Okay, so we have d theta dt, and all it was really was 1 step away from the information that was given. Now the question we have is, how fast is the passenger rising? Like, what is his vertical velocity? Okay, well, let's figure out at that moment where the passenger is first, okay? Now, if he's 42.5 feet above the ground, if we subtract the 30 feet here, that means that the passenger is 12.5 feet above the ground. 12.5 feet above the center of the Ferris wheel. If that's the case, that means that he is halfway up in terms of the radius. Because if this whole radius is going to be 25, then 12.5 is right in the middle. And right in the middle winds up being, right, pi over 6, doesn't it? Because, pi over 6 is going to have that ratio, right? It's going to have the 12.5 and the 25. Okay. So, and of course the 12.5 is conditional information. This 25 doesn't change. This is our y. This right here is our x. But in terms of the conditional information, we should note that if we basically lay a Cartesian plane on top of the Ferris wheel, making the center of the Ferris wheel the origin, this angle right here is my theta. And what I'm really looking for, if I set it up this way, and this is the easiest way to do it, is I'm looking for dy dt when, conditional information, when y is equal to 12.5. Well, when y is equal to 12.5, the implied conditional is that theta is pi over 6. And we could find our x value. This is 25 times 1/2. The x value, of course, would be 25 times root 3 over 2. And so it would be 25 root 3 over 2, or 12.5 times root 3. Okay, well, let's go ahead and figure it out now. Now, I need to basically figure out a way to represent this so that I can actually find dy dt. Now, eventually, how fast is he moving horizontally? We're also going to be asking for dx dt, okay? But for our purposes right now, first of all, let's do it with y. Well, I want to use this constant right here. I certainly don't want to use another variable. So let's do sine of theta is equal to y over 25 feet, right? And therefore 25 feet times sine theta is equal to y gives us a nice equation where we can now differentiate. So 25 feet times cosine of theta d theta dt is equal to dy dt. Well, that makes it pretty easy. Dy dt is then simply 25 feet times cosine, because at that moment, right, remember that theta is pi over 6, cosine of pi over 6 times d theta dt, which is pi radians per minute. Now remember, radians as sort of a pseudo unit is going to evaporate. Cosine of pi over 6, like we've said before, is root 3 over 2. So my dy dt is 25 pi root 3 over 2, and the radians disappear, and that's feet per minute. By the way, if you care, that approximates to about 68.017 feet per minute. Now, if we were going to then do it for the horizontal distance, it would be roughly the same thing, right? We would just have to set it up. And let's go ahead and use another sheet of paper since this is going to get crowded otherwise. Instead of sine theta y over 25, it would be cosine theta is equal to x over 25 feet. 20, and of course we're going to do the same thing. 25 feet times cosine of theta is equal to x, and therefore we can differentiate from there. Now remember, the derivative of cosine is negative sine times d theta dt is equal to dx dt. And of course we can go ahead and turn this around, and we get dx dt is equal to 25 feet times negative sine of pi over 6 times, and of course d theta dt, as we realized, is pi radians per minute. This, of course, sine of pi over 6 is 1/2, and this is negative, so it becomes negative 1/2. And so we're going to get negative 25 pi over 2 feet per minute. Now, why is this one negative? Well, it's negative because we've designated this as the center, and as somebody swings around this way, x, of course, is shrinking. So in the real sense, he's not, going a negative rate. He's going 25 pi over 2 feet per minute. But in terms of the way that we've set it up, our x value in this particular scenario is shrinking as the guy kind of goes around that way. Now, that is how we find dy dt and dx dt. Yay us. Let's go ahead and move on to another example. A plane flying with a constant speed of 300 kilometers per hour passes over a ground radar station at an altitude of 1 kilometer and climbs at an angle of 30 degrees. So what happens is you have the ground, okay? You have a radar station, and I'm not going to try and draw any sort of radar. That's that little box. And a plane, the moment that the plane actually is over the radar station, it starts to climb at an angle of 30 degrees, okay? Which is, let's ish it, looks kind of like that. Okay. So you have a plane heading that way. And you know that if this right here is 30 degrees, then this whole thing right here is 30 plus 90, it's 120 degrees. Now, at what rate is the distance from the plane to the radar station, increasing 1 minute later. Now, first of all, you're given, okay, and let's designate this right here as A, although we know A, it is 1 kilometer. Let's designate this as B, and let's designate the distance between the radar station and the plane as C. Now this, of course, is a whole lot like the Falcon question that we got, but let's go ahead and do it. What we have here is we have 300 kilometers per hour, but notice we have a little problem right there. So if my dB dt is 300 kilometers per hour, then I need to figure out how many kilometers that is per minute. And it winds up being 5 kilometers per minute. Sorry, per hour. Okay. And I needed to do that because it's talking about 1 minute later. Okay. So the question is the distance between the plane and the radar station. That is, at what rate is C increasing? Okay, now our condition is after 1 minute. But after 1 minute implies a particular value for B that implies a B value of 5. Right? Because if it's after 1 minute and it's going 5 kilometers per minute, then it's going to be 5 kilometers. Now, from there, we can use the law of cosines to find C. Okay, so we know that C squared is equal to A squared plus B squared minus 2AB cosine C. In this particular case, that C squared is equal to 1 squared plus B, or actually at that point it actually is a value, 5 squared minus 2 times 1 times 5 times, now cosine of 120 degrees, we've already talked about this, is -1/2. Now that negative and the negative cancel out, the 1/2 and the 2 cancel out, and I'm left with C squared is equal to 1 plus 26 plus, or 25, sorry, jumping the gun a little bit, 25 plus 1, or 31. So C is equal to the square root of 31 kilometers. And that's somewhere between 5 and 6 kilometers, right? Okay, so this was just getting your conditional information. Now I need to use this exact same equation. I need to differentiate it. I need to basically plug in what I need to plug in, differentiate it in order to find my dc dt. So let's go ahead and we have C squared is equal to 1 kilometer squared plus B squared minus 2 times 1 kilometer times B times cosine of 120 degrees. Well, let's go ahead and clean that up. Let's actually get rid of the units. I know what the units are going to be, but the units are just going to crowd us out here. Basically, cosine of 120 is, of course, -1/2. The -1/2 cancels with the -2, and I'm just left with B. So, I mean, you can reorder this if you want. It doesn't really matter. So when I take the derivative, I'm going to get 2c dc dt is equal to 2b plus 1 db dt. And now I have everything that I need. I know that dc dt is going to be equal to 2b plus 1 over 2c times db dt. So let's go ahead and plug in. I know that b is 5, so 2b plus 1 is 10. I know that c is root 31, so it's 2 times root 31. And I know that, of course, because b and c will be the same units, those units will cancel out, and the only units that will really matter is the ones coming from my dB dt, which is up here, which is 5 kilometers per minute. I have 5 kilometers per minute, and that, you can simplify a little bit, and you wind up with 25 over root 31 kilometers per minute. And of course we can get a decimal approximation for that, so let's go ahead and do that. Because we certainly don't want to rationalize the denominator. That's just a waste of time. Okay, and that winds up being 4.490 kilometers per minute. And if you remember, in the Falcon problem, the Falcon was, the rate of the Falcon was 88 feet per second, and the rate at which the distance between them was 81 and change. So the rate at which C was expanding was a little bit less than B. We have the same geometry here in terms of it being a 120-degree angle right here. So the fact that this is increasing at a rate a little bit less than the dB/dt actually basically accords with the problem that we did earlier that was similar. Now, let's go ahead and do another one. Woohoo! All right, a clock one. The hands of a clock are 2 inches and 3 inches long. See the figure. As the hands move around the clock, they sweep out the triangle OAB. At what rate is the area of the triangle changing at 12:10 p.m.? Now, you need to remember that what's implied in this scenario is how fast each of those hands goes around. Now, of course, the minute hand, okay, is 1 revolution per hour. The hour hand, okay, is 1 revolution every 12 hours. So that winds up being 1/12 of a revolution per hour. Well, that means that in our given, and of course we can talk about the minute hand, and basically we'll basically just talk about it like this. The minute hand, if it's 1 revolution per hour, that is 2 pi radians per hour. And this is 1/12 of that. So it winds up being pi over 6 radians per hour. Now at 12:10, okay, the minute hand is going away from the hour hand. And the minute hand is sweeping out at 2 pi radians per hour. The hour hand is following it. So if we're going to talk about this theta measurement right here, d theta dt is the difference between those, because the hour hand, as slow as it is actually creeping along a little bit and lessening that full 2 pi radians per hour. So my d theta dt, just based upon what I know about a clock and what's happening to the hour and the minute hand at the time of 12:10, I know that my d theta dt is 2 pi minus pi over 6. So that's going to be 11 pi over 6 radians per hour. Okay, well that's kind of interesting, because I know that the area of an oblique triangle we can get from 1/2 AB sine C. Okay, well in this case it's 1/2 2 3 sine theta. Or, since those two cancel out, A is equal to 3 sine of theta. Okay, well let's differentiate and see whether I have everything that I need. 3 cosine of theta d theta dt. All right, well the only thing that I really am lost with is cosine of theta. I need to figure out what the theta is here at that particular moment at 12:10, because I have the rest. Now the question is, how am I going to do that? Well, you know that if it sweeps out pi over 6 radians per hour and 2 pi radians per hour, you know how, well, you already know how far the minute hand is, right? The minute hand over here has swept out from the 12, it has swept out pi over 3, right? So because it's, 1, 2, 3, 4, 5, 6, it's 1/6 of a revolution. 1/6 of a revolution is pi over 3. The problem is that theta is not pi over 3 because you have to take into account that itty-bitty angle that the hour hand has swept out. Okay? And if it has swept out pi over 3 in those 10 minutes, okay, then basically what needs to happen is you need to figure out in those 10 minutes how much did the hour hand sweep out. Well, if it's pi over 6 radians per hour and it's gone for a 1/6 of an hour, it's pi over 36. So theta, yeah, this is sort of a complicated one because so much of it is just dependent upon what you know about clocks. So much of it is implied. So you need to find dA dt. We've already sort of figured that out. But another one of our conditions, our conditional information is implied by the time. The time is 12:10, and our theta is going to be pi over 3 minus pi over 36. So that's 12 pi over 36 minus pi over 36, or 11 pi over 36. That is the theta value, which should make sense because it's just a little bit less than 1/6 of a revolution, right? So from here, we know that dA dt is equal to 3 cosine 11 pi over 36 times d theta dt, and our d theta dt is 11 pi over 6 radians per hour. Okay. Let's go ahead and plug that in, cosine, and we'll go ahead and use our ratio to make sure we don't make a keystroke error, over 36 times 3 times, and we'll do another ratio again to make sure we don't make a keystroke error, over 6, and boom. Okay, that means that the area is changing. Okay, now remember, these are inches up here. These are inches up here, and those inches were included right here. I just didn't write them down, right? When you put the 2 and the 3 in here, you got inches squared. So it's inches squared per hour. That's a pretty tough one, right? Because I mean, the hardest part is realizing that because is getting the d theta and the theta, knowing that both the minute hand and the hour hand are moving, and having to account for both of their movement in order to find the d theta and the theta. Now, kind of annoying, yes, but kind of neat. So I hope you enjoyed that. It's the end of our trig-based problems videos. If you have any questions, please do shoot me an email. Bye.